seniors who survived calculus. We're two seniors. I can't breathe. And I'm Grace Mayer. We're two seniors who survived calculus and want to help you do the same.
Taking derivatives is an important step in calculus, but that's just the beginning.
Now that you know how to derive, you can use that knowledge to learn more about a variety of functions.
Today, we are going to discuss two of these applications. We will start with finding the absolute and local extrema with the extreme value theorem.
We will then move on to the mean value theorem, which connects the instantaneous and average rates of change over function, and show you how you can apply that.
Now we've got a lot to cover, so let's get started.
Woo! Maximum! Minimum! You're going to have to learn to find maximum and minimum values if you want to survive in calculus.
Yeah, we know you learned that in pre-calc. Just pressing a few buttons in your calculator, right?
Wrong!
A calculator was just fine back then when you were little pre-calc padawans. But you're beyond that now.
So throw that machine straight into the Sarlacc pit. Get rid of it.
No,
that's a terrible idea. Don't do that. You will need your calculator later. You will actually need it later in this section, so
just not now.
Just not now.
Okay. Yeah.
Do we want to do that one more time?
I'm good with it.
Okay.
It's just bad and dumb.
You want me to rewrite it?
No, I love it.
Before you can find extreme values, it's important that you understand the extreme value theorem.
This theorem states that any function that is continuous on a closed interval is guaranteed to have a maximum and minimum on that interval.
These conditions cannot be relaxed. If the function is not continuous or the interval is not closed on both ends, the function could fail to have both a maximum or a minimum.
The extreme value theorem isn't particularly useful on its own, although it will show up occasionally on the AP test, so you should be aware of the conditions needed for it to apply.
But once you understand the theorem, you can find that the extrema for almost any function. We extremely value this theorem.
Shut up. These maximums and minimums can occur in two places, at endpoints and at critical points.
What is a critical point, you ask? Let me tell you. A function has a critical point anywhere that its derivative is 0 or does not exist.
Not every critical point is a maximum or minimum. They could also be a corner or cusp, removable discontinuity, jump, asymptote, or vertical tangent. But frequently, a critical point will be a function's maximum or minimum, or at least a local extrema.
These local or relative extrema occur when a function changes directions. They may not be the highest or lowest point, but they are higher or lower than the surrounding points on either side.
An absolute extrema occurs at a function's very highest or very lowest point.
Let's take a look at a simple function and see if we can apply the extreme value theorem to find its absolute extrema.
Take the function f of x equals 1 over x plus ln of x on the closed interval from 1/2 to 4.
According to the EVT, this function is guaranteed to have both a maximum and a minimum.
To find these values, you first have to take the function's derivative and find the function's critical points.
The derivative of this particular function is negative 1 over x squared plus 1 over x. This would be undefined when x equals 0, so 0 is technically a critical point, but since it's outside of the domain, you can disregard it.
Critical points also occur when the derivative is 0. If you set the derivative we got equal to 0, you can work it out to 1 over x equals 1 over x squared. So x squared equals x, making x 0 or 1. We already discarded 0, but now that we know 1 is a critical point, we'll want to make sure to check that one.
Remember, on a closed function, the endpoints could also be a maximum or a minimum, so we have to check 1/2 and 4 as well.
To check these numbers, plug them into the original function. You may need your calculator for the number crunching on this part, but a graph won't be necessary. You should get f of 1/2 equals 1.307, f of 1 equals 1, and f of 4 equals 1.636.
Now, you just look at the outputs. The maximum occurs when the output is at the greatest, and the minimum when it's at the least. So, in this case, the maximum of the function is 1.636, which occurs at 4, and the minimum is 1, which occurs at x equals 1. 1.307 would also be a local maximum in this case.
Why don't you try one on your own?
You have the function f of x equals 4x minus x squared plus 6. What are its absolute maximum and minimum values on the closed interval from x equals 0 to x equals 5?
We're going to show you some puppies now while you work it out. We'll give you the answer in a couple of seconds.
Pause the video if you need more time.
Here's the answer!
The maximum is 10, occurring at x equals 2. The minimum is 1, occurring at x equals 5.
I'm sorry I wrote so slowly, you guys. You just have to deal with it. Lots of love.
Love.
So there you have it, the extreme value theorem in a nutshell.
Almost entirely unrelated, but equally important, is the mean value theorem.
This theorem provides the connection between average and instantaneous rates of change.
The mean value theorem states that for any function that is both continuous on a closed interval and everywhere differentiable, then at least one point along that interval, the derivative of that point, is equal to the average rate of change between the two endpoints.
So, if a function is continuous on the closed interval from a to b, and differentiable everywhere on that interval, then at some point c, f prime of c equals f of b minus f of a, divided by the difference between b and a.
Think about a car driving along a stretch of highway. If you start at the 0-mile marker and it takes 2 hours to get to the 100-mile marker, then your average speed was 50 miles per hour. At some point, even for a split second, you must have been going exactly 50 miles per hour to make that the average speed.
The conditions, like for the extreme value theorem, cannot be relaxed, or the point at which the rates of change are equal may not exist.
If the function is not continuous or not everywhere differentiable, you cannot apply the mean value theorem.
For example, this theorem wouldn't apply to an absolute value function if the corner were included in the interval, because then the function has a point of non-differentiability.
Bad.
Or, if the function has some form of discontinuity, like a hole or a vertical asymptote, you can't apply the mean value theorem. There's the hole.
Bad. Okay.
A corollary of the mean value theorem is Rolle's theorem, which states that if f of a equals f of b and all the conditions for the mean value theorem apply, then at some point c, f prime of c equals 0.
This is another theorem that doesn't tell you much on its own, but once you know that this point C exists, you can use your calculus wisdom to find it.
Let's try an example with the mean value theorem.
Start with the function f of x equals x squared on the closed interval from 1 to 6. At what point C does the instantaneous rate of change equal the average rate of change?
First off, always make sure that the mean value theorem applies.
In this case, we're good. Continuous closed interval everywhere differentiable. Finding the average rate of change is just finding slope. So find f of x is 36, and f of 1 is 1, and 36 minus 1 over 6 minus 1 equals 7, making that your average rate of change.
Now, take your function's derivative to find instantaneous rate of change. The derivative of x squared is, of course, 2x.
Now, set the two rates of change equal to each other, replacing the x with a c. So, 2c equals 7. Then solve for c, giving you 3.5.
Meaning that the point x equals 3.5 satisfies the mean value theorem for derivatives. The instantaneous rate of change at that point is equal to the average rate of change over the given interval.
Now it's your turn. Try and find all the points that satisfy the mean value theorem for the sine wave on the closed interval from 0 to 2 pi.
Pause the video while you work it out. We'll show you a few more pictures of dogs in the meantime.
Here's the answers.
The points pi over 2 and 3 pi over 2 satisfy the mean value theorem for derivatives on this function on this interval.
The extreme value theorem and the mean value theorem help to set you up for the basic applications of derivatives. They are both extremely useful and extremely helpful.
Extremely. Make sure you understand the conditions needed to apply these theorems and know what the theorems are and how to use them. Review that before your AP test if you want to be successful.
Thanks for watching. I'm Siri Dove.
I'm Grace Manor, and good luck on your calculus quest.
This isn't a quest.
It's totally a quest.
I can't reach it.
Use the force.